Hello, students. In this video, we're going to discuss intermolecular forces, the different types, and their relative strength. And intermolecular forces influence physical properties of matter. They influence, and some of us have heard of it, in hydrogen bonding. So it influences why water has such a high boiling point, or why DNA is a double-stranded helix. So these are the type of things that impact us around the world. So we need to break down these intermolecular forces to help us understand why things are found in the phases they're found in and certain properties. So first we got to talk about electrostatic forces. Electrostatic forces are the attractive forces between positive and negative charges. So you can think of primarily protons in the nucleus and electrons in the electron clouds orbiting the nucleus. So every molecule in matter experiences two types of electrostatic forces. Again, attractive forces between positive and negative charges. So typically you first learn what are the intramolecular forces. Those are the forces within molecules. I tell students this is basically your ionic and covalent bonding. Okay, so those are the forces you primarily talk about. They're within closer proximity and they determine chemical reactivity. And why is that? Well, for a chemical reaction, I have to break bonds and form new bonds. So what were those bonds? Ionic and covalent. Intermolecular forces, and again, we're using this prefix, is the force between molecules. So remember, international flight between countries, intermolecular forces between molecules or particles. These forces determine physical properties and they influence them. So that's kind of the focus of this video. So intermolecular forces, and essentially these are going to originate from interactions or electrostatic forces between charges, partial charges, or temporary charges. The other thing we have to take into account is intermolecular forces are much weaker than intramolecular forces. So the strongest intermolecular force is still weaker than an intramolecular force because it's between molecules and the distance is far compared to within molecules. So the potential energy is still higher because they're further apart. So the best example is to look at two water molecules. Now we know that this represents oxygen and this represents a hydrogen and this is a covalent bond. It's an overlap between unfilled orbitals. So basically oxygen's contributing one electron and so is a hydrogen. This relative distance of 96 picometers is much closer than the distance between these molecules in general. So this is a stronger electrostatic force, and that is referred to as a polar covalent bond. Now it's polar because there's a difference in electronegativity between the oxygen and the hydrogen. The oxygen's more electronegative, so it pulls the electrons away, and it's creating a partial positive charge on this hydrogen and a partial negative charge on that oxygen. So with a neighboring molecule, this oxygen is partially negative, and this hydrogen is partially positive. So this partial negative charge is attracted to this partial positive charge. And that's what I mean by partial charges. Now, the intermolecular force is weaker because the distance between these partial charges is larger than the distance in this actual covalent bond. So it'd be 96 picometers versus 204 picometers seen between the oxygen and the hydrogen. This 300 is between the two oxygens. So that's what we're going to focus on. So what are the different types of intermolecular forces? We got dispersion forces. So dispersion forces are all atoms are going to experience this. Why? Every atom or molecule has electrons and protons. So they're going to be attracted to their neighbors' electrons and protons. Dipole-dipole forces are the predominant intermolecular force in polar molecules. So if I'm a polar molecule, I can experience dipole-dipole and dispersion. but the dipole-dipole is going to be stronger. Everybody's heard of hydrogen bonding. Hydrogen bonding is the predominant force in polar molecules where hydrogen is bound to a nitrogen, oxygen, and or fluorine. So that is key. You have to have a hydrogen bound to one of these three very electronegative elements, and they're also very small. So it makes that distance between the molecules closer, lowering the potential energy, making that attractive force more stable and harder to break. And then there's the ion dipole. So when we think about dissolving salts in water, we see that with the ions dissociating and separating into their relative cations and anions and being surrounded by the water molecules. So essentially, this is kind of an example of that. So we have the dispersion forces, and we have, this is representing an H2 molecule where you have the nuclei here, and the electron cloud with the two electrons are there. And here would be a neighboring molecule. And then with the dipole forces, again, it has to be a polar molecule. So I see the partially negative chloride lining up with the partially positive hydrogen. With hydrogen bonding, now I have to be bound a hydrogen to either fluorine, oxygen, or nitrogen. And now I can distinctly see that the fluorine is much smaller than this chlorine. So now this intermolecular force is going to be much stronger because the relative distance between these molecules is much closer. And then the ion dipole is where we talk about, solvation. When you talk about the surrounding of the solvent molecule around the solute, we see that a positive cation is surrounded by the water molecule's partially negative oxygen. So this is a quick summary, but I want to go in greater detail so that we fully understand this. Dispersion forces is present in all molecules and results essentially from electrons moving around, right? So the electrons are moving around, they're not static. So these movements can cause dispersion forces. This is referred to as a instantaneous dipole. That is a vocabulary term that you need to know in chemistry. So what do I mean by an instantaneous dipole? If I took helium, and if you look on the periodic table, helium is, 4-2 pretty much. What does that mean? The 2 represents the atomic number, the number of protons. The 4 represents the mass, which is the number of protons and neutrons. In this picture here, we're going to just make it easy. Here is my nucleus, but we know that we have 2 protons in it. These are my electrons, which are negatively charged. So I have negative charges and I have positive charges, okay? If I was to take a picture of helium at any moment, we know that there's a probability map, because of quantum theory, where the electrons are going to be found. So at one moment in time, the 2 electrons might be here. If I take another picture, they might be there. And, typically they're going to want to, because they repel one another, be apart. But there might be a time when I take a picture, and in this one frame of this picture, the 2 electrons are on one side of this probability or electron cloud, probability map. So when the negative charges are on one side of the atom, what I get is a partial negative charge. Now over here, because there's no negative charge, and all you really see on this backside are the positive protons in the nucleus, this gives me a partial positive charge. Now, this happens frequently because the electrons are always moving around, and every instant, it's possible that there's an instantaneous dipole. So what does this mean? Well, the instantaneous dipoles, okay, it doesn't happen all the time, but when it happens, it's going to create a charge separation in the neighbors. This is referred to as an induced dipole. So basically, once an instantaneous dipole occurs, it can force an atom or molecule next to it to have its own instantaneous dipole. but it's referred to as induced because it's causing it to happen. So if I had that previous helium atom for one instant where the electrons are on one side and I create a partial negative and a partial positive, as another, I said hydrogen, I'm sorry, helium. As another helium atom approaches this one, the electrons are going to be pulled in this direction in this electron orbital cloud because they're attracted to the positive backside of that helium. And then if another one approaches, the same thing, the electrons are going to move towards the neighbor's positive induced dipole. So that's an induced dipole. We started with an instantaneous dipole here, which forces a neighboring atom to create a induced dipole or dipole temporary at that time. So the dispersion force strength is actually influenced by two factors. One, the polarizability of the electrons. So what does that mean? Polarizability is the ability for the electrons to move. So the larger the volume of an atom, so we know that as I have more protons in the nucleus, I end up getting more electrons. And if I have more electrons, they start fitting into more and more energy levels. As I get more energy levels, the volume of the atom is larger, and now the movement is over a greater distance, and they're more polarizable. So dispersion forces are influenced by the polarizability of these electrons for these instantaneous dipoles. Just think of it as this way. More electrons, greater probability of an instantaneous dipole. So a larger molar mass means more electrons, a larger electron cloud, increased polarizability, and more instantaneous and induced dipoles, resulting in a stronger dispersion force. The other thing that affects London dispersion forces is the actual shape of the molecule. So if there's more surface area per volume, there's going to be a more surface-to-surface contact, and as a result, more instantaneous dipoles, resulting in more induced dipoles. So what does that mean? Stronger attraction. So the two things that really influence dispersion force is the molar mass and the shape of the molecule. So that's why Lewis dot structures are so important. We got to be able to draw the shapes of these molecules. So let's first look at the size of an atom and look at the strength of the dispersion forces. So we'll take noble gases, and we know they're all nonpolar. So that's really simple. So here is an example. So I have helium going down on the noble gas, group 8A or 18. I go down to xenon. And what I notice is the molar mass increases because I'm packing on more and more electrons in these energy levels. And as I pack more and more electrons, this volume of the electron cloud gets bigger, which means now the electrons are easily polarizable. And because there's more electrons that can move around and polarize, there's more instantaneous dipoles and there's more induced dipoles on the neighbor. So what the result is the boiling point we can see increases. So why does the boiling point increase? Well, to boil liquid to gas, I have to separate, right? Because gases take up a large volume and the particles are far apart. I have to separate the particles in the liquid phase to become a gas. Well, to separate them, I have to overcome those electrostatic forces that we call intermolecular forces. So it requires more energy if the intermolecular force is stronger, because I have to disrupt it and separate them. You can think of it as a stronger magnet. It would take more energy to separate. So the stronger the attractive force, the higher the boiling point. So we can clearly see this on a boiling point chart when we're comparing straight chain alkanes. Remember, alkanes are carbons bound to either other carbons and hydrogens, all in single bonds. We learned basic organic nomenclature. The and means a straight chain. They all end in ane because they're all carbon single bonds to either other carbons and hydrogens. 5 means pentane. So C5H12, right? We look at that, it has a certain molar mass, and we see that it has a certain volume. C6H14, hexane, it has a larger molar mass because essentially I'm adding a CH2. So it goes up by 14. So and actually I can calculate, so C5, right, there's 5 carbon, each carbon is 12, right, and then there's 12 hydrogen. Each carbon has a mass of 1, right, so 5 times 12 is 60, right, and then plus 12, the molar mass is 72, so that's why that's right here, it's roughly 72. And then the next one, you add 14 is going to be 86, and that's why it's right there. But going to hexane, what we notice is the molar mass is increasing, right? Because I'm adding another carbon and another 2 hydrogens. So what happened? The boiling point increases. When I go to heptane, I have an increase in molar mass. So what happens? An increase in boiling point. I can see that there's a direct relationship between molar mass. As molar mass increases, right, it's directly proportional to the boiling point. The boiling point increases. What about shape? Okay, well, let's compare things that have the same molar mass, but a different shape. Well, just like we learned in organic chemistry, we could have pentane, which we see is 1, 2, 3, 4, 5 carbons. You could also draw it like 1, 2, 3, 4, 5. It's okay, they're showing you the hydrogens. But what we see in a straight chain is there is more direct contact, more overlap. So there's a larger surface area. In neopentane or 2,2-dimethylpropane, because this is more spherical, right, its shape doesn't allow as much stacking. There's not as much stacking here in contact. Because it's more spherical, there's less contact. So less contact means less electrostatic forces, right, and less intermolecular forces. So as a result, the N-pentane has a much higher boiling point than the neopentane. So that was London dispersion forces. Now let's talk about dipole-dipole force. So again, all molecules exhibit London dispersion forces because they have electrons that can be polarized and they have protons in the nucleus. With dipole-dipole, that can be an additional force that polar molecules exhibit. So in polar molecules, because they're polar, there's a permanent dipole. We don't have to wait for an instantaneous dipole to occur. So the attraction is a permanent dipole and it's always present. So let's look at formaldehyde. We know that this carbonyl in this aldehyde, right, in methanal or formaldehyde, is polar. Why? Oxygen is very electronegative. In fact, the value is like 3.5. And carbon is electronegativity is 2.5. So that's a difference of electronegativity of 1. So that's a big difference in electronegativity. That creates a dipole where the oxygen is pulling the electrons and the bonds towards itself and away from carbon, creating a partial positive on the carbon and a partial negative on the oxygen. Well, what does that mean? It means it's a permanent dipole. So permanent dipoles can line up. So I can have the partially positive carbon be attracted to the partially negative oxygen in a neighboring formaldehyde. And that dipole, that interaction is always present because they're permanent. So how does this affect intermolecular forces? Well, again, polar molecules, they have dispersion forces, but they also have the additional dipole-dipole that becomes the predominant force. And then that strength is much stronger when we're comparing polar molecules with non-polar molecules of the same size. So here's an example. I have formaldehyde, which we just discussed had the permanent dipole due to the carbonyl and the carbon having a partial positive and the oxygen having a partial negative. When I compare it to ethane, which ethane again is an alkane, right? It's just carbons with single bonds to other carbons or other hydrogens. Both of them have molar masses of roughly 30 grams per mole, or 3 atomic mass units if I look at individual molecules. But what I notice is even though they have the same mass, because we saw that as molar mass increases, so does the intermolecular forces. But if they have the same molar mass, why would they have different boiling points? Well, what we realize is because they have different intermolecular forces. The polar molecule formaldehyde can exhibit dipole-dipole as well. And how does that influence the boiling point? Well, it's kind of confusing to see because these are negative values, but we can think of it as this way, right? Which one is closer to 0 degrees Celsius? Formaldehyde. So what does that mean? It requires more heat energy to boil formaldehyde. So why does it require more energy to boil formaldehyde and separate the molecules of formaldehyde from one another? That's easy. It has a stronger intermolecular force. It's harder to disrupt that dipole-dipole intermolecular force and separate those formaldehyde molecules. Now we can see the same effects that we saw with London dispersion forces shapes, right? With dipole-dipole. Okay, so this diagram is excellent because what it's showing me is I have roughly in all of these 44 grams per mole, but the dipole moment, or we can think of it as, the difference in electronegativity or the polarity of the molecule, or just basically based on how polar it is or polarizable the electron cloud is, it's going to affect the boiling point. So the thing that has the lowest boiling point of all of these is propane. Why is that? It's all carbon to carbon or hydrogen single bonds. This is a non-polar molecule. It can only exhibit London forces. So it has the lowest boiling point. Then I go to dimethyl ether. Now dimethyl ether, this is where your Lewis dot structures really help, right? If I draw a dimethyl ether, it has this bent shape, right? And it's polar because it has that oxygen, and the bond between oxygen and carbon, there's a difference in electronegativity. So because dimethyl ether is polar, its predominant intermolecular force is dipole-dipole, which is stronger than just London dispersions that we see in the propane. Because again, propane is all non-polar bonds, right? Just carbons with a bunch of hydrogens. So this has a higher boiling point because it has a permanent dipole. Now with the ethylene oxide, it's hard to see this, but this is actually a fixed cyclic structure. So it's a rigid structure, okay? So even though the molar mass, because to combine this structure, I actually lose 2 hydrogens to make it a fixed ring. Even though it has a decrease in molar mass, why is it that the boiling point increases? Well, it still exhibits dipole-dipole, and it's, if you look at it, polar bond is right there. But the fact that it's a fixed cyclic structure means that it's easier to stack. Because remember, single bonds can rotate. So because this is a more rigid structure, there's more surface to surface area contact. More points of contact means stronger intermolecular forces. When I go to acetaldehyde, what do I notice? I have a CH3, and now I have an aldehyde, which means I have that carbonyl on the end. So again, this has a lower molar mass than the dimethyl ether. Why is it that it has a higher boiling point than the ethylene oxide, which is an ether, and this ether? Well, if we look, one of the things that makes the carbonyl so polar, so now it's even more polar. It has that carbon-oxygen bond, which is, again, there's a large electronegativity difference, right? So it's polar, but Because of the double bond, remember, we talked about this when we discussed hybridization, that single bonds really are sigma bonds, which is a direct internuclear overlap. And the pi bond, so if I was to draw these bonds, there's my sigma. The pi bond is perpendicular to the sigma bond, and it's above and below that in what's referred to as a pi cloud. And that pi cloud is loosely held because it's not directly between the nuclei. It's perpendicular, it's above and below. So what does that mean? That pi bonds are more polarizable. So if they're more polarizable, that means you're going to have a stronger intermolecular force and a stronger dipole. And where do we see that? Well, now we go to acetonitrile. And acetonitrile, right? We have that methyl group. And now we don't have one pi bond. We have a triple bond in the nitrile right here in the C triple bonded end. And what we notice is now there's one sigma bond and two pi bonds. So the two pi bonds mean more polarizability. So it's even more polar, a greater dipole moment. So it even has a stronger dipole intermolecular force, and it has a largest boiling point. Man, I'm geeking out about this. I'm getting all pumped up. But now we still need to talk about hydrogen bonding. And, really, hydrogen bonding is a complete misnomer. It's not an actual bond. It's not covalent. It's not ionic. It's not an intramolecular electrostatic force. It's an intermolecular force. So why does this happen? The highly electronegative and small elements of nitrogen, oxygen, and fluorine really pull the electrons away from hydrogen, so it almost creates a positive charge on the edge of a molecule. So that's why I refer to it as a super dipole. So we see this where? In ethanol, right? So ethanol, we see, right? We have a carbon here, a carbon here. It's hard to see, but this is a CH3 and then a CH2 and then your OH. They do a better job showing you the H's here. But we see that we have the oxygen bound to a hydrogen. So right there, because I have that oxygen bound to a hydrogen, I have an extreme polar bond. And that extreme polar bond creates almost like this positive charge on the edge of this molecule right here. And it's going to be attracted to the oxygen that's bound to this hydrogen in that super dipole or permanent dipole. And that force is extremely strong. And that explains why water has such a high boiling point for such a low molar mass. It's because it can just super dipole all over the place. And in reality, each water molecule can exhibit 4 hydrogen bonds. So you can have 2 lone pairs here, right, that are attracted to these partially positive hydrogens right here. And really above here, I could have 2 more hydrogen bonds because there could be a neighboring oxygen right here in a water molecule. So there would be another hydrogen bond. And then this could be next to another water molecule, oxygen right there. So each water molecule can exhibit 1, 2, 3, 4 hydrogen bonds. That's a lot of hydrogen bonding. So that results in really strong intermolecular forces. So the effect of hydrogen bonding, well, if you can do a super dipole, you're going to have a really strong intermolecular force. And they have way higher melting and boiling points than you would even expect. So how can we test this? Well, we can take molecules of the same molar mass, because remember, we talked about intermolecular forces being influenced by molar mass and shape. And what we notice is because of this oxygen, it's going to have a different shape. We know that this is bent. It's not tetrahedral. It's a bent shape, and it's very polar. But it's a super dipole because the hydrogen's bound to an oxygen. So what does that do? super dipole, hydrogen bonding, the boiling point exceeds expectations and is way higher than a normal ethane that can only exhibit London dispersion forces. So let's do a quick check to make sure we understand the intermolecular forces present. So if we look, this is where it really helps you to be able to draw Lewis dot structures. Now, hydrogen bromide, if we look at hydrogen bromide, right? There's 3 lone pairs on the bromine, and then there's 1 covalent bond, but it's polar covalent, so that's dipole-dipole. When we look at iodine, right? It has a single bond, 3 lone pairs on each iodine, right? So we look at this is a non-polar bond, dispersion forces, or London forces. We look at carbon monoxide. Well, what do we have? It's a polar bond with 1 sigma and 2 pi clouds, dipole-dipole. Again, remember the pi clouds, very easy to polarize them because they're not held between the 2 nuclei. Ammonia, hydrogen bonding. How did I know that? Well, we got a lone pair and we got a bunch of hydrogen bound to one of the 3 electronegative elements that it needs to be bound to have hydrogen bonding. Remember, those 3 are nitrogen, oxygen, and fluorine. What about silicon tetrachloride? That's dispersion. Why? Because this is a symmetrical tetrahedral molecule. Well, there's lone pairs here. I'll just omit it because it just takes too long. And this video is probably, a long time. So what if I was comparing these two? All right. So dimethyl ether versus propane, similar molar masses. Which one would have the higher boiling point? The dimethyl ether. Why? It has a polar oxygen and it can exhibit dipole-dipole. And we can see clearly here that the boiling point is much higher. In this, why is it that the methylmethanamine has a higher boiling point than propane? Well, it contains a polar nitrogen, but more importantly, it can hydrogen bond. Why do I know it can hydrogen bond? Well, I have a hydrogen there, I have a CH3 there, and a CH3 there, and a lone pair. And this bond right here allows me to hydrogen bond. And I see a big increase in the boiling point. Like even if I compare it, right, because this molecule is polar, the dimethyl ether, but its boiling point is lower. Why? Because this can only dipole-dipole, right? Why does this only dipole-dipole? Well, again, with a dimethyl ether, remember, the oxygen's not bound to a hydrogen, it's bound to a carbon, right? Here, the hydrogen's bound to a nitrogen, so it can hydrogen bond. What about ethanol versus that N-methylmethanamine? The ethanol has a higher boiling point. Why? Because it can actually hydrogen bond more times than this one can. It can actually hydrogen bond 3 times versus this can only hydrogen bond once, 2 times. Or you can think of it as the oxygen is more electronegative than the nitrogen, so the hydrogen bonding is stronger. And we see a very big increase because the hydrogen bond is stronger because of the difference in the electronegativity. And there's more hydrogen bonding. The reason why there's more hydrogen bonding is if I draw ethanol and I look, right? The oxygen has 2 lone pairs. So remember, and this hydrogen, so I could have 1, 2, and then this 3 hydrogen bonds because there could be an oxygen right here for a neighboring ethanol. Over here, there could be a hydrogen from a neighboring, ethanol, and 1 over here as well. So you could have 3 H bonds versus 2 H bonds. Now, the last but not least is ion dipole attraction. So this is when we dissolve things and we talk about heats of solution that we learned in thermochemistry, and we can take the temperature changes of the surroundings to estimate the heat of solution, basically the heat of solving, because what you're basically doing is you're breaking the bonds in the sodium chloride salt, and you're making hydrogen bonds. Again, that's a misnomer, but you are making these attractive electrostatic forces. They're intermolecular, but still. So why does that happen? Ion dipole attraction. So we see that the negatively charged anion chloride is surrounded by the partially positive charges of the water molecule. That's termed the surrounding of the solvent, right? After the dissociation of the ions, the surrounding of the solvent is what we refer to as soluble, right? Or dissolving, right? These terms, you've heard them all along, right? Solubility rules, dissolving. I even refer to it as solvation. Why? Why is it solvation? The surrounding solvent is surrounding the ion. Well, over here, what happened? Well, the sodium ion's positive, so it's surrounded by the partially negative oxygens. So the ion dipole attraction is even stronger than the hydrogen bonding. So when we look at the different types of intermolecular forces, we've already discussed dispersion, all molecules exhibit. If you're nonpolar, you can only exhibit dispersion forces. Dispersion forces, like all forces, get stronger with an increase in molar mass and with more surface area. Dipole-dipole happens with polar molecules, and it's stronger. So if I have a polar molecule and a nonpolar molecule of similar molar mass, the polar molecule is going to have a higher boiling point because the dipole-dipole is a stronger intermolecular force. Then I have hydrogen bonding, which is the super dipole, but the hydrogen has to be bound to one of these three elements directly, and that's even stronger. And then the strongest is what we see in mixtures, right? And when we dissolve things is between the solute and the solvent, and we refer to that as ion dipole. So I hope this video makes sense. I hope you have a better foundation and understanding of intermolecular forces and how they influence how things are attracted to each other and what their relative strengths are. Thanks so much for watching, and let me know if you have any questions.